So now today we will start, yesterday also in the last lecture we have started our unit number 6, shear and torsion. Now in this unit we have to design the beam specifically for shear and torsion. Okay, up till now what we have done, we have designed the beam only for bending moment and shear force. So in the bending we considered like it is only the bending moment about z axis. We have not considered the bending moment along the longitudinal axis, that is along the length of the member. So here we need to consider both of them, that is your bending moment along z axis and your bending moment along longitudinal axis, that is your regular bending moment and your twisting moment, or we can call it as a torsion. Okay, so combinedly we are going to design the sections, and for combining the bending moment and twisting moment we are going to consider a equivalent moment. There is a concept of equivalent moment. This equivalent moment can be calculated by adding the bending moment to torsional moment, okay, or from subtracting the bending moment through torsional moment. So what we need to do, I will explain you now. So here, suppose now this is our beam. Okay, what we regularly do, this is beam. So in the beam now, suppose now this is the stirrups, okay, which are provided. And if I draw the reinforcement, then normally we provided reinforcement like this. Here at the bottom we provide the bars. Okay, and at the bottom whatever we provide the reinforcement, this is nothing but this is your stirrups. Okay, for what we are stirrups provided, we are providing the stirrups for shear reinforcement. We always provide the stirrups for shear reinforcement. Okay, then these are the stirrups, and these are the bars which we provided normally for bending moment. Okay, from MU, depending upon the MU, we provide these bars. Okay, and at the top normally we provide at the top what, 2 bars of 10 mm or 12 mm. This is our regular design. Okay, this is our regular design. Now the key point over here is what I want to show you. So here now see these 3 bars, we always provide the bars are at bottom for the bending moment MU. If you know the diagram, suppose now if I draw this beam here, okay, suppose this is a beam, and then suppose these are the supports of the beam. Then under the loading condition, suppose arbitrary loading is acting on the beam. Okay, so this is loading. Under this condition, this beam will deflect, or the bending moment shape will be like this. Okay, so tension is at bottom. So for to resist this tension, this steel is provided. To resist this tension, this steel is provided. And how this moment is, this is nothing but your bending moment MU. Okay, this is in normal regular beams. Okay, now see in the case of these beams, the beam subjected to shear and torsion. Now again I will draw the section over here. Suppose now, and I will draw the stirrups. So these are the stirrups, and then I will show you here the reinforcement at bottom. These 3 bars. So as I told you earlier, these bottom bars are designed for the bending moment, sagging bending moment. Okay, this bending moment must be sagging bending moment. Here you can see the profile. Okay, in this diagram, here you can see the profile here. This bending moment must be sagging bending moment. For that we provide the bars at bottom. Now here in this case, here these 3 bars for shear and torsion, these 3 bars are designed for the bending moment ME1. This ME1 is nothing but this ME1 is called as equivalent bending moment. Okay, this ME1 I will write here, ME1, this is called as equivalent bending moment. Okay, and ME1, from this ME1 these 3 bars are designed. And how do we calculate ME1? The formula to calculate ME1 is equal to MU plus mt. Okay, mu plus mt, where mu is your bending moment. Okay, where mu is your bending moment, and again this mt, you can calculate this mt as mt is equal to, again there is one more formula to calculate the mt, and this mt it can be calculated as tu. Okay, tu, just a moment, it is calculated as tu in bracket 1 plus d by b divided by 1.7. This is the formula. All these formulas are given in IS code. You don't worry about the formulas. Just to understand what I am trying to tell you. Are you understood this? What is happening in normal beam? In normal these beams, where that we have not considered the torsion. In that, in this case, the steel at the bottom it is designed for the bending moment mu, and this bending moment is sagging bending moment. Okay, but in this case now when the beam is subjected to shear and torsion effect, combined effect, then these bars are not designed for this bending moment mu only. Okay, this is the difference. These bars are not designed for this bending moment mu only. These bars are designed for equivalent bending moment, that is me1, and this me1 it can be calculated as me1 is equal to mu plus mt. So in this bending moment mu you have to add something mt, and what is this value mt? This mt is again calculated as tu in bracket 1 plus d by b divided by 1.7, where tu is the twisting moment or torsional moment, d is the overall depth of the section, b is the width of the section. Okay, this is the basic difference between these two. Okay, and now this condition is valid. Okay, when, okay, this is when your mu is greater than mt. Okay, when your mu, this value of mu is greater than mt, then you can only calculate the value of me1. Okay, we are only calculate the sagging bending moment. There is no need to calculate the hogging bending moment if your mu is greater than mt. And in this case, at the top, we are going to provide the, in this case now, in this case, when your mu is greater than mt, we are going to calculate only me1. Okay, the sagging bending moment. There is no need to calculate the hogging bending moment, for which we are going to provide the steel at top. So in this case, when your mu is greater than mt, we will design the beam only for the moment me1, and at top we will provide the nominal reinforcement, that is 2 bars of 10 mm or 2 bars of 12 mm. This is the case when your mu is greater than mt. Okay, but reverse also can happen. Sometimes you may come across the case where your mt is greater than mu. Okay, when the case is reverse now, suppose when the case is reverse, that is when your mt it is greater than mu. When this case arises, then in this case now you have to calculate the hogging moment also, and that hogging equivalent moment it can be calculated as me2. The notation for hogging moment is me2, and it can be calculated as mt minus mu. Mt minus mu. If mu is greater than mt, there is no problem. You are going to calculate only mu1, and you will provide the nominal reinforcement at the top. But when your this mt is greater than mu, then you need to calculate that remaining moment. That remaining moment which acts in the opposite sense of me1, and that moment can be calculated as me2 is equal to mt minus mu. Okay, and whatever may be the moment comes mt minus mu, for that moment we need to design these top bars. Okay, these top bars are designed for this moment me2. I hope now you are clear with this, what we need to do. Okay, for your simplicity now I will explain once again. Pay attention, this is the only difference. If you understand this, there is nothing in this chapter. This is the easiest chapter of DCS1, very easy chapter. Okay, just you need to understand this. I will tell you once again. Up till now what we have done, or what we did, we have designed the beams. Okay, while designing the beams we provide the steel at bottom and steel at top. In normal beams I am talking about, there is no torsion considered. Then what we normally do, we design these bottom bars. We design these bottom bars for this bending moment mu. Okay, this bending moment we may calculate at WL square by 8 or by different coefficients. By using those, we calculate this bending moment, and for that bending moment, by using the formula of AST, we provide these bars normally. Okay, and if it is singly reinforced section, then at top 2 bars of 10 mm and 2 bars of 12 mm we usually provide. If it is doubly reinforced section, then at top also we provide the area of steel in compression that you already know, you have studied. This is in the case of normal beam. Now when the beam is subjected to combined shear and torsion, so in that case now the basic difference is these bottom bars, here these bottom bars are designed for the moment mu, but here in this case these bottom bars should be designed for the equivalent moment me1. This is called as equivalent bending moment, and the value of this me1, it can be calculated as me1 is equal to mu plus mt. Okay, mu plus mt, this is the formula. And mt is equal to, further mt is equal to tu1 plus d by b divided by 1.7. This is the formula to calculate mt, where tu is the torsional moment, d is depth, b is width. This is you already know. Okay, now up to this point this is okay, but there are two conditions. The first condition is when mu is greater than mt. This is the first condition. Okay, and second condition is when mt is greater than mu. Okay, so now in the first condition, when mu is greater than mt, you just calculate me1, and for that me1 provide the steel at bottom and provide at top nominal reinforcement, that is 2 bars of 10 mm or 2 bars of 12 mm, like in this case which is provided, if this case is there. And now if the reverse case is there, if your mt is greater than mu, okay, if your mt is greater than mu, then what we need to do? Then you have to calculate this moment me2. This is the hogging moment which is developed at the top, me2. So me2 is nothing but it is mt minus mu. So difference between these two, whatever the remaining moment is there, for that moment you need to provide these parts, okay, by using the formula of AST. So very simple thing. This is the basic difference between what we can say normal beam, what we design usually, and the beam subjected to combined shear and torsion. Okay, so next we will write down some theory. You also uh, take down it. So first of all, write down the formula for equivalent shear. Okay, equivalent shear. Equivalent shear. So normally in normal beams we calculate the shear, that is shear force, and that formula is Vu is equal to whatever may be the shear force WL by 2 or whatever something it may be there, or by using the coefficient we calculate the shear. But in the case of now equivalent shear, your formula is, for equivalent shear it is is equal to VE is equal to Vu plus 1.6 Tu upon B. Okay, Tu upon B. And this formula is given in IS 456 2000. This formula is given in IS 456 2000. Clause number 41.3.1, 41.3.1, page 75. Page 75. Okay, so this formula is given, and they have also elaborated this formula, that is V is equal to equivalent shear, Vu is equal to shear force. Okay, so V is equal to equivalent shear, Vu is equal to shear force, 1.6 is your constant, Tu is the twisting moment or torsional moment, and B is the width of the section. So on this page, now page number 75, this formula is given, so there is no need to by heart this formula. We require to calculate the equivalent shear. Now here also you see the word here is equivalent shear. We are not only calculating the shear force. Now we are calculating this equivalent shear by considering the torsional effect also. Here you have considered the term Tu. Means indirectly what you are doing, you are also considering the twisting moment effect or torsional effect in this shear. Okay, so this is your normal shear, and in that you are adding this torsional effect plus. Okay, in ME1 also. ME1 is equal to what is the formula? MU, that is your original bending moment, plus MT. That plus MT is nothing but additional moment or addition of torsional effect. Okay, so this is the formula for equivalent shear. Now after the equivalent shear, we will calculate nominal equivalent shear. Okay, so nominal nominal equivalent nominal equivalent shear. Okay, so nominal equivalent shear, again the formula is same. Tau VE is equal to, it is VE upon BD. This formula we have used many times. You know that tau V is equal to VU upon BD. Instead of that, just you have to add the term equivalent. Okay, equivalent nominal shear, or you can say nominal equivalent shear, which is equal to equivalent shear divided by area. Divided by area. Okay. So now take down the important points. I am going to give you important points. You write these points with me. These are very important. Based on these points, our whole design is based. Okay. So first we will write down the points. Then I will tell you, and I will also show you in the IS code where these formulas are given and from where we are taking the values. Okay. So I will write. You also write with me. So the first important point. Okay, so if the equivalent nominal shear stress, if the equivalent, simultaneously you should also write down, if the equivalent nominal shear stress, if the equivalent nominal shear stress tau VE, that is this shear stress tau VE which is mentioned above, does not exceed tau C, that is permissible shear stress. Okay, permissible shear stress given in table number 19, given in table number 19 of IS 456-2000, then the minimum shear reinforcement, the minimum shear reinforcement, then the minimum shear reinforcement is required as per as per so it is as per clause number 26.5.1.6, page 48, page 48. Okay, of IS 456-2000, of of IS 456-2000. Okay, so I will read this for you. So what they have said, if the equivalent nominal shear stress tau VE, means this stress, equivalent shear stress is tau VE, which you are calculating by VE upon BD. This is your nominal shear stress, equivalent nominal shear stress tau VE, does not exceed tau C. Means the value of tau VE is less than tau C. The condition what they have told about us here is, here if you see this tau VE is less than tau C. That is what they are talking about over here. Okay, so if this is the condition tau C, and from where do we calculate tau C? This is, you already known that we always calculate this permissible shear stress from table number 19. Okay, so tau C, then the minimum shear reinforcement is required as per clause number 26.5.1.6 of page number 48. Okay, so on the page number 48, the formula for minimum shear reinforcement is given, and that formula is ASV minimum is equal to tau VE minus tau C B into SV divided by 0.87 FY. Okay, later on we will see that formula. Just now I have told you the formula orally, but you understand this. Okay, so when this is applicable, when your tau v, this value of nominal shear stress is less than the permissible shear stress, so there is no need to design the shear reinforcement in this case. So the minimum shear reinforcement we should provide, and this reinforcement can be provided by using the clause 26.5.1.6 page number 48. Okay, so this formula we will see later on. I have already told you the formula, but we will see it later on in the IS code where the formula is exactly given. This is the first important point. Now if you your writing is completed, then we will move to the second point. Is it over? Is it over? Okay, so now next important point is our next important point. Okay, so the next point is if tau v exceeds tau c. Okay, if your nominal shear stress tau v, if your nominal shear stress tau v exceeds exceeds tau c, okay, tau c, the reinforcement is required. Then the reinforcement the reinforcement is required, which consists of which consists of which consists of so it consists of a longitudinal reinforcement longitudinal reinforcement and B transverse reinforcement transverse reinforcement. Okay, so now see what they have given. Okay, so if tau v exceeds tau c, now what does this condition talk about here? Now what does this condition talk about here? If I write over here the conditions which they have given the condition that your tau VE now it is greater than tau C. In previous condition here your tau VE is less than tau C. Here your tau VE is less than tau C. If you see this, here we have considered tau VE is less than tau C. If this is the condition, then you should go by this clause, whatever given over here. Now the condition is this one, your tau VE is your tau VE is greater than tau C. This is what is the condition given over here. Tau VE is greater than tau C. So for that you need to design the longitudinal reinforcement as well as transverse reinforcement. If you come across this condition that your equivalent shear stress is greater than permissible shear stress, okay, then we need to design the longitudinal reinforcement as well as transverse reinforcement. Okay, now see how to design the longitudinal reinforcement first. So I will give the next heading longitudinal reinforcement. Okay, so a longitudinal longitudinal reinforcement. How to design the longitudinal reinforcement in this case? Okay, so now the longitudinal reinforcement. The longitudinal reinforcement shall be designed. Okay, you write down simultaneously with me. The longitudinal reinforcement shall be designed to resist an equivalent bending moment, an equivalent bending moment ME1 ME1 which is given by we can write the formula ME1 is equal to, I have already explained this to you, MU plus MT. Okay, so the longitudinal reinforcement shall be designed for this. ME1 is equal to MU plus MT. Okay, so let me know if you finish. We will move to the next part. So now we will move to the next part. So this is about longitudinal reinforcement, how we are going to design the longitudinal reinforcement. So here I can further add to this. Okay, here if you write further, where MT is equal to where MT is equal to, what is the formula for MT? I have told you, TU in bracket 1 plus, it is overall depth divided by width and whole divided by 1.7. By using this formula you can calculate the MT. Okay, so here one more important note we will write, if here MU is greater than MT, then bottom steel should be designed for the equivalent bending moment ME1, okay, and and at top nominal reinforcement reinforcement should be provided. Okay, if your MU is greater than MT, then at bottom steel, the word steel is remained over here. I will write bottom steel. Okay, the bottom steel. So the bottom steel should be designed for the equivalent bending moment. Okay, bottom steel should be designed for the equivalent bending moment and equivalent bending moment ME1. Okay, that equivalent bending moment is nothing but it is ME1, and at the top nominal reinforcement should be provided. So nominal reinforcement means 2 bars of 10 mm or 2 bars of 12 mm. That is our nominal reinforcement. Okay, now the second case, if, okay, I will write here if here MT is greater than MU. Okay, so the first case was MU is greater than MT. Okay, so this is your first case. This was your first case. Okay, now the second case is different. Okay, so this is your second case now. This is the second case. So here in the second case, then the moment Me2 is being taken is being taken taken into the account, which is calculated as which is calculated as this also I have already told you. Me2 is equal to, it can be calculated as mt minus mu. Okay, mt minus mu. Okay. And the important thing is, yeah, I will write over here. I will write steel for this moment. Steel for this moment Me2 should be provided at top. Should be provided at top. Okay, here bracket complete. Should be provided at top. So steel for this moment should be provided at top. Okay. So write down the things. If it is over, let me know. We will discuss about shear reinforcement. So all this is about longitudinal reinforcement we have talked right now. Okay. Okay, so the next is the shear reinforcement. So the next B, A is over now, longitudinal reinforcement. Now part B, that is shear reinforcement. That is shear reinforcement. Okay, so for the shear reinforcement, the shear reinforcement can be calculated as follows. So the formula for shear reinforcement is ASV is equal to, it is TU into SV, okay, whole divided by this divided by B1 D1 into 0.87 Fy, okay, 0.87 Fy plus VU into SV, again whole divided by 2.5 D1 into 0.87 Fy. So write down up to this point. I will explain you later on what is this. This is the formula. This formula is also given in the IS code. This formula is also given in the IS code. Write down up to this point first. The shear reinforcement can be calculated as follows. So ASV is equal to, ASV means what? Area of stirrups. That is, if you consider two-legged 10 mm, we are going to use, where this TU is your twisting moment, SV is the spacing, ASV is the area of the stirrups, 0.87 is constant, Fy you already know, Fy is yield strength of steel. Then this B1 D1 is the horizontal center to center distance between the bar, and D1 is the vertical center to center distance between the reinforcement. So B1 is horizontal center to center distance between the reinforcement, and D1 is vertical center to center distance between the reinforcement. I will explain you what is B1 D1 while solving the numericals when we come to that part. Okay, so at that time I will tell you what is B1, what is D1. Okay, now, but there is again one more thing they have included over here. This is your reinforcement. Okay, but there is clause for minimum reinforcement also. So you can calculate the reinforcement by using this formula. But also here I can write but total shear or transverse reinforcement. Total transverse reinforcement. Total transverse reinforcement shall not be shall not be less than, okay, shall not be less than, so ASB is equal to, so the minimum reinforcement shall not be less than, so ASB is equal to tau VE minus tau C. Now these two terms already known to you, equivalent nominal shear stress and permissible shear stress, okay, divided by divided by okay, so divided by 0.87 Fy, 0.87 Fy into B into SV, where B is the width of the section and SV is the spacing. So this is the formula, this is the formula to provide the shear reinforcement or transverse reinforcement. Okay, but at the same time you should check that this provided transverse reinforcement should not be less than this value. Okay, should not be less than this value. Okay, so that we need to consider. Okay, so what we are going to do, we will calculate the spacing by using this formula also. We will calculate the spacing using this formula also. Okay, and what is the minimum value out of these two, that value we will adopt. Okay, so in this way now we need to design the beams for combined shear and torsion. I think this much theory is sufficient for you. So formulas are given on page number 75, page number 48. Almost all the formulas are given. Still, we will see if the formulas are there or not. Okay. Ah, so okay, so we will go to page number 75. Okay, so page number 75, we will see how many formulas are given over there on that page. Okay, so here you can see on page number 75, if we go, if we see all these formulas are given. Okay, on page number 75, here is the first formula. Okay, this formula, see here, V is equal to VU plus 1.6 TU by B. Okay, this formula is already given over here. I will put rectangle against those formulas. So this is the formula which I have already told you. Okay, shear, each and every term is given below. What is tau V? Okay, see here, if you see at the bottom, each and every term is given over here. What is VE, what is VU, what is TU, and what is B. Okay, and also what needs to do, it is going to be the equivalent nominal shear stress tau V in the case shall be calculated from 41.4. Okay, so what is the value and what all those things, and from the table number 19 also what to do, everything is given over here if you read this carefully. Okay, whatever I have told you just now, by simplifying that, everything is given here if you go through this. Then the second thing is, this formula. Me1 is equal to mu plus mt1. Okay, this formula is also given. Me1 is equal to mu plus mt. Okay, and this mu is the bending moment at cross section. Mt is equal to tu into 1 plus d by b 1.7. This formula is also given in the IS code. Okay, whatever formula we are using, everything is given in the IS code. Now if we move further, then see at the top here also. See, if you read these clauses carefully now, this whatever this is given over here, if you read this carefully, that is the things which I have explained you right now in another different way. Okay, what to do and what not to do. So here also that this is also given. You see, if you see over here, then this is also given ME2, the calculation of ME2 and how the ME2 is going to be calculated. So this is the formula for ME2, how to calculate the ME2. Okay, and here they have mentioned that it is in opposite sense of the MU. If you read the bottom line, here in the bottom line they have explained that this MU2 is being taken acting in the opposite sense to the moment MU. Okay, so mu moment we always take it as a sagging moment. Okay, so this is in the opposite sense, means it is hogging moment. So that is why we are providing steel at top. Whatever steel we got from mu2, that should be provided at top. Here also they have given flexural compression phase. So the reinforcement whatever you have got from this reinforcement shall be provided. Okay, here they have given, if you read it carefully, flexural compression phase. So flexural compression phase. In a normal beam, we consider that the tension is at bottom and compression is at top. Okay, so at that phase now we need to provide this steel, whatever we got from this Me2. Okay, so now if we move further, then they talked about this transverse enforcement also. So about the transverse enforcement also, here the clauses are given. See the transverse enforcement. Okay. So the transverse reinforcement, it can be calculated as. Okay. So this is the formula which I have already told you right now. If you see, ASV is equal to TU divided by V1 D1 0.87 Fy plus VU SV 2.5 D1 0.87 Fy. Okay, this is the shear reinforcement. By using this formula, we are going to calculate the spacing of the shear reinforcement. Okay, and but the total transverse reinforcement here also the formula which is next to that. But the total transverse reinforcement shall not be less than this formula. This is also I have given you just now. Tau VE minus tau C B into SV divided by 0.87 Fy. Okay, and if you go below, see here, if you come here below, what they have given, the meaning of each and every term. Tu is the torsional moment, Bu is the shear force, Sv is the spacing of stirrups reinforcement, B1 is center to center distance between the corner bars in the direction of the width. Okay, I think this is clear to you now. B1 is the center to center distance between the corner bars in the direction of width, means horizontal center to center distance between the two bars. Okay, then D1 is the center to center distance between corner bars. Okay, so D1 is the center to center distance between the corner bars. So this distance is in the direction of width, this distance is D1 is in the direction of depth. Okay, so B1 we are going to measure horizontally, D1 we are going to measure vertically. Then B is the width of the member. Then this is the characteristic strength Fv. Then tau Ve equivalent shear stress. Okay, this is already specified in the earlier clause over here. Then tau C is the shear strength of concrete as per table number 19. So they have specifically told you tau C you should take the shear strength of concrete as per table number 19. Okay, so these are the terms which we need to consider over here. Okay, and now we will go to this page number 48 also. Page number 48. I am searching, is there any formula is there, so that you should be aware of this. Okay, so the minimum shear reinforcement for stirrups, that formula is given over here, ASV upon B into SV should be greater than 0.4 divided by 0.87 Fy. Okay, these are the clauses of shear reinforcement. See here, what I want to tell you, the important clause. Uh, See, this is distribution of torsion reinforcement. This is the important thing, and this distribution can be done by using this formula here. If you see, okay, so what they have told, when a member is designed for torsion, torsional reinforcement shall be provided as below. A. The transverse enforcement of the torsion shall be rectangular closed stirrups placed in perpendicular to the axis of the member. The spacing of the stirrup shall not exceed, okay, exceed the least of. So this is very important line. If I underline this, okay, if I underline this, the spacing of the stirrups, okay, the spacing, this line, the spacing of the stirrup shall not exceed the least of, okay, the spacing of the stirrup shall not exceed the least of x1 comma x1 plus y1 by 4 and 300 mm. ओके, त्यांनी काय सांगितलंय की हे जे तुम्ही स्पेसिंग देणार आहात स्टिरप्सचं, हे स्टिरप्सचं स्पेसिंग या तिघांमधली लिस्ट व्हॅल्यू पाहिजे. जे काही तुमचं स्टिरप्सचं स्पेसिंग असेल, इट शुड बी द लिस्ट व्हॅल्यू आउट ऑफ दिस 3. ओके, म्हणजे पहिले दोन तर स्पेसिंग आपण ऑलरेडी काढलेले असणार आहेत फॉर मिनिमम रिइन्फोर्समेंट. That formula I have already told you. In addition to this, you need to calculate the spacing by using these three things, and the minimum value of all these 5 you should adopt. Okay, so the minimum value where x1 and y1 are respectively short and long dimensions of the stirrups. Okay, so x1 and y1 are the long and short dimensions of the stirrups. How to calculate this? I will tell you while solving the problem. How to calculate x1, how to calculate y1, and also in the previous formula how to calculate b1 and how to calculate d1. These things we will see while solving the problem. Right now you understand and you take a overview of this, what the codal provisions we are going to use, and all the formulas are there in the IS code. You just remember, for this unit number 6 you should go for on page number 75 and page number 48. That's it. या दोन पेज जर तुम्ही फक्त बघितले की तुमचं युनिट नंबर 6 संपलं, ह्याच्या बाहेरचं तुम्हाला काहीही येणार नाही. ओके, डिझाइन करायला. ओके, सो नाउ by using all these formulas, now we will proceed for solving the numericals. Okay, so start the numericals. We'll start to solve the numericals. So I will write down the problem, you write it simultaneously with me, and then we will try to solve it. Okay, so now write the problem with me. One more thing, there is only one type of problem which is asked in the examination for this unit, and दूसरा कुठला problem याच्यावर बनूच शकत नाही. Okay, so this type of problem is going to ask you in the examination. Only thing is that sometimes you need to calculate ME2 in some numericals, or in some numericals you don't need to calculate ME2. Okay, that is the only difference. So now I will write the problem over here. So now write down the problem and let me know after the completion of the problem. So I will read the problem for once again. Determine the reinforcement required for rectangular beam with following data: width of the section 300 mm, depth of the section 600 mm, factored bending moment 80 kilonewton meter. So here they have given factored bending moment, so there is no need to multiply this bending moment by 1.5. Okay, they have already given you the factored value. Factored or ultimate means they have already multiplied it by factor of safety 1.5. So factored bending moment is given, factored twisting moment is given. So twisting moment is also factored value is given to you. Okay, so there is again no need to multiply it by 1.5 over here. And factored shear force is also given to you. So again the same thing is that factored word is there. So we will take these values as it is. Then M15 and Fe415. These are the grades. So M15 is the grade of concrete, Fe415 is the grade of steel. Now see how to solve this problem and how to move further. So here what I will do now, we are going to assume the clear cover, then we are going to assume the bar diameter for reinforcement, and then we are going to assume the bar diameter for the stirrups also. Okay, so here what I am going to do, so assume clear cover is equal to 25 mm. I will assume clear cover is equal to 25 mm. Then bar diameter for main reinforcement, then bar diameter for main reinforcement, I will assume this reinforcement as 20 mm bar diameter. Okay, then bar diameter for stirrups, bar diameter for stirrups, I will assume this bar diameter as 10 mm. Okay, so these are the values which we have assumed now. So they have given us the beam section, and beam is this width, that is the section is of 300 by 600. Okay, so if you see this section they have already given to us. If I draw over here, this section already they have given to us, and what they have told that these lengths from this point to this point, and these are the given dimensions, and this is given as 300 mm, and this total it is given as 600 mm. Okay, so these are the given values with us. So this is the overall depth is known to you. Okay, so now overall depth capital D is equal to 600 mm. So from this now we are going to calculate the this effective depth D. So now to calculate the effective depth, see here in this now in this beam the stirrups are also going to be placed. Okay, so the stirrups are also here somewhere, and the diameter bar, those will be placed at here at the bottom. Here maybe the bars are placed. So your effective depth must be, your effective depth if you need to calculate, then that must be from the center of this bar. Okay, from here. So that value should be, I show you from top to this point. This value we need to calculate. This is nothing but your small d. This is nothing but your small d, effective depth. Okay, so now I will tell you what we have assumed. We have assumed bar diameter for this stirrup. For this stirrup, we have assumed the bar diameter 10 mm. Okay, now for these internal bars, these bars, we have assumed the bar diameter as 20 mm. Okay, and what is the cover? So we assume the clear cover as 25 mm on this side and 25 mm on this side also. Okay, now if you calculate the effective depth D, then this total is 600. So I will write over here 600. Now 600 मधनं काय होणार पहिल्यांदा? So from this 600 we need to minus this 25 first. Okay, we need to minus the 25 first. So this 25 we need to minus first. After this 25 we need to minus this bar of 10 mm diameter. Okay. After this 10 mm diameter bar, we should take half of this main bar. Okay, so these three things we need to minus. That is your clear cover. Then this is the bar which is of the stirrups, and this is the main reinforcement. So if I do it, then what do I get? 600 minus 25. This is my clear cover. Minus 10. This is the stirrups bar diameter, and minus 20 by 2. So if you do, then you will get the effective depth. And what is the value of this? What is the answer? 555. Okay. So your effective depth is 555 mm. So this is your effective depth. Okay. Now we will move to the next point. That is equivalent moment. Okay. Equivalent bending moment. So equivalent bending moment. Okay. Equivalent bending moment. We call this as ME1. This is your equivalent bending moment. So how do we calculate ME1? ME1 is equal to MU plus MT. So we need the value of MT. So therefore we will calculate the value of MT first. So MT is equal to, if you don't remember, go to page number 75. You will see the formula of this MT. So here you can write from IS 456 2000 clause number so and page number 75 MT is equal to. In that way you should write in the examination. Okay, I have already shown you where this formula is there in the I score. So MT is equal to, it is TU in bracket, we can write 1 plus D by B whole divided by 1.7. This is the formula. So therefore MT is equal to, just put the values over here. TU, what is the value of TU? Now either you put all the values in kilonewton meter or either you put all the values in Newton mm. So I will go for kilonewton meter. You can also put the values in Newton mm, there is no problem, but you make sure that the unit of every quantity is same. Okay, so now TU, I think the value of TU factored किती दिली होती? What was the value of TU? It is 40 kilonewton meter. So the value of TU given is 40 kilonewton meter. So it is 40 into 1 plus capital D. So capital D is 0.6. In meter I am going to take 0.6 divided by B is the width of the section. B is 0.3 and whole divided by 1.7, close this bracket. So which is equal to, let me know the value of MT. .38. Okay, so the value is 70.38 kilonewton meter. This is the value of MT. 70.58 ka? Okay, so 70.58 kilonewton meter. So I will make the correction. 70.58. All of you please check the value. This, it is right or what? So now after the calculation of MT, it is very easier for us to calculate ME1. Okay. So now therefore, okay, correct value. So therefore, therefore ME1 is equal to MU plus MT, which is again equal to Mu plus Mt, which is again equal to Mu. So what is the value of Mu given in the problem? So if I see here, the factored bending moment is 80 kilonewton meter. The factored bending moment is 80 kilonewton meter. Factored bending moment is nothing but your Mu. Okay, this is nothing but the value of mu. This is mu. So this is 80 plus 70.58. Now do the calculation. What is the answer? It is 150.58. Okay. The answer is 150.58 kilonewton meter. Okay. So here you check the value. Who is greater, who is less. Okay. So that it is confirmed for us to calculate the ME2 or not. Okay. So now if I check over here. So here what is happening? Here mu. What is the value of mu? The value of mu is 80 kilonewton meter. And what is the value of mt? So if you see mu, the value of mu here, the value of mu is 80 kilonewton meter. Okay. And what is the value of mt? The value of mt is 70.58 kilonewton meter. Okay. So who is greater now? So we can easily say that mu is greater than mt. Okay. And whenever mu is greater than mt, then what we needs to do? Whenever mu is greater than mt, then there is no need to calculate the me2. Okay. So here I can write nominal nominal reinforcement nominal reinforcement shall be provided nominal reinforcement shall be provided at top. Okay, nominal reinforcement shall be provided at top. So at top we can provide 2 bars of 12 mm or 2 bars of 10 mm. Okay, so we can go for 2 bars of 12 mm. Okay, as there is no need to calculate ME2, so we can provide the nominal reinforcement at the top. So I can write over here. Otherwise we will write that afterwards also or here also. So here you can write provide 2 bars of 12 mm diameter at top. So we will provide 2 bars of 12 mm diameter at top. Okay, this sentence you can write here itself also or at the last also, it doesn't matter. Okay, so now after this the important thing is remaining, that is check for depth. Check for depth. We need to take the check for depth. So to take the check for depth, equating maximum bending moment to moment of resistance. So your maximum bending moment is 150.58 into 10 to the power 6, which is equal to 0.138 FCK B D required square. Okay, D required square. So therefore, D required is equal to, what is the value? Calculate this D required. I think you are knowing, so that is why I have erased that formula. You know that how to calculate now. So many times we have used the formula. So the answer is 880.73. 880.73 mm square. All please check the value. Is it the right answer? AST. Give me the confirmation. If this value gets wrong, then everything gets wrong. So please confirm it. Otherwise our problem will get wrong if the value is wrong. Is it the right answer? The formula is AST is equal to 0.5 FCK BD divided by FY in bracket 1 minus under root 1 minus 4.6 MU upon FCK BD square. So there at the in place of MU you need to put the value 150.58 into 10 raised to 6. So answer is confirmed 880.73. So we will move forward. Now we have assumed 20 mm bar diameter. So calculate the number of bars. So the number of bars is equal to 880.73 whole divided by pi by 4 into 20 square. So how many bars required? Calculate the number of bars now. Okay, so the number of bars are 2.8. We round up this to 3 numbers. 3 number of bars. Okay, we did 3 bars. Okay, so calculate AST provided now. AST provided, so which are equal to 3 bars of 20 mm diameter, 3 into 5 by 4 into 20 square. So let me know the value of AST provided. 942.47, 942.47 mm square. Okay, correct answer 942. So this is our AST provided. Okay, so here I can write finally, therefore provide 3 bars of 20 mm diameter at bottom. Okay, 3 bars of 20 mm diameter at bottom. That is what we have provided. Now calculate the percentage of steel. PT, percentage of steel. How do we calculate percentage of steel? It is 100 into AST provided, 100 into AST provided whole divided by BD. So put the value and calculate the answer. So it is simple, 100 into AST provided is 942.47 whole divided by B into D. B is 300 into D is effective depth is 555. From this you will get the value of percentage of steel. What is the percentage of steel? So it is 0.56%. Okay, so 0.56%. This is our percentage of steel. Okay, so up to this point now what we have done, we have calculated ME1, we have checked for the condition. Okay, we have checked for the condition that our MU is greater than MT or MT is greater than MU. So based upon that condition we have provided 2 bars of 12 mm diameter at top. Correct, am I right? 2 bars of 12 mm diameter at top, and based on the bending moment value ME1 we have designed the bottom bars, that is 3 bars of 20 mm diameter at the bottom, and for that we have calculated the percentage of steel. Okay, so this completes your part of longitudinal reinforcement. Now we will go equivalent shear reinforcement. Okay, so we will calculate now equivalent shear. So equivalent shear, the notation is VE, and it can be calculated as VU plus 1.6 TU by B. This is the formula. So therefore VE is equal to VU. Now what is the factored shear force? Value of factored shear force, it was given in the problem now. So that value is how much? I think 70, it may be 70, correct me if I wrong, and it is factored value, so there is no need to multiply it by 1.5. Factored value 70 plus 1.6 TU. TU is the twisting moment, so the value of twisting moment is it is given as factored value 40, so into, here it is in the bracket, 40 by B is 0.3, because you have taken these values in kilonewton meter. So I'll put bracket over here. This calculation you need to do first. So here bracket must be there only, so that your value must be right. So the answer is 283.33. So your equivalent shear is 283.33 kilonewton. So this is the value. Okay, 283.33. That is equivalent shear. Now calculate equivalent nominal shear stress or nominal equivalent shear stress. Now calculate nominal equivalent shear stress. Now if this is completed, then next is nominal equivalent shear stress, tau VE. Okay, so tau VE is equal to, it is VE divided by BD. So if you just put the values, what was the value previously? It is 283.33. So 283.33, 283.33 divided by B is 0.3 into D is 0.6. So calculate this value. So instead of this, now we will take it in Newton mm. That will be much more easier for us. Okay. This is also right value because this force is now in kilonewton and these dimensions are in meter. So you will get the stress in kilonewton per meter square. And afterwards we need to convert that into Newton per mm square. So instead of that, now we will, it's here itself we will put the values in Newton mm. So it is 283.33 into 10 raised to 3. Okay, and in mm we can write over here 300 into 600. So if you solve this, you will get the value in Newton mm. What is the value? 1701.7. Answer Newton per mm square मध्ये answer सांगा मला. 1.57. Okay, so 1.57 Newton per mm square. So 1.57. D is okay, right. Here we should take effective depth. So D must be 555. 555 घेऊनच केलेलं आहे ना 1.57 or it is 1.7. Do it. See, this D is nothing but small d. Small d is the effective depth. By mistake, I have written over there capital D, that is 600. It should not be that like that. You should take 555. Okay, 1.7 is the right answer. Okay, I will correct here. So our answer is 1.7 Newton per mm square. Now is it right? 1.7. So it is 1.7 Newton per mm square. This is the answer. Okay, 1.7. So now we need to go to table number 20. Now open your IS code and go to table number 20. Okay, and calculate the value of tau C max for M15 grade of concrete. For M15 grade of concrete. Okay, for M15 grade. Okay, go to table number 20. Table number 20. And let me know the maximum value of tau C max. The value of tau C max. Maximum permissible stress, that is ultimate. त्याच्यावर व्हॅल्यू गेली की तुम्हाला सेक्शनच रिवाइज करावं लागणार. ओके, देर इज नो एनी अदर प्रोव्हिजन. तर ही tau C max ची व्हॅल्यू मला सांगा. फ्रॉम टेबल नंबर 20 आय एम सेइंग, डोंट गो फॉर टेबल नंबर 19. I am asking you maximum permissible stress. You go to IS code and see table number 20. Or shall I do it over here? Okay, we will go to table number 20 in the IS code. Okay, So IS code table number 20. We need to search it. It may be somewhere near to the page number 70, 73. Okay. So this is table number 20 now. If you see. So this is table number 20. What that table shows, the maximum shear stress tau c max in Newton per mm square. Maximum shear stress. So what they have given us, they have given us here the grade of steel M15, M20. So the grade of steel is given over here M15, M20, M25, M30, M35, M40 and above. And the maximum shear strength or the maximum shear stress, it is in Newton per mm square, and these values are given for M15 2.5, M20 I think 2.8, 3.1, 3.5 and so on. Okay, so now for our interest the value is this value. Okay, this value we should take into the account. For M15 the value is 2.5. आता हे का बघायचं, तर ह्याचं रिझन असं आहे की when you calculate the value of tau VE, okay, this tau VE value should be always less than tau C max. Okay, if this tau VE value is greater than tau C max, जर ही व्हॅल्यू जास्त आली या 2.5 पेक्षा, तर तुमचा सेक्शन हा फेलच होणार आहे. तुम्ही किती शिअर एन्फोर्समेंट द्या. आर यू गोइंग टू गेट माय पॉइंट. जर समजा इथं तुमची जर ही व्हॅल्यू इफ युअर टाउ VE इज ग्रेटर दॅन टाउ सी मॅक्स असं जर आलं, तर यू ऑलवेज नीड टू रिवाइज द सेक्शन. असं जर आलं तर तुम्हाला सेक्शन काय करावं लागणार आहे, रिवाइज करावं लागणार आहे. ही जर केस आली तर का, तर तुम्ही ह्या कंडिशनला तुम्ही कितीही हाय शिअर एन्फोर्समेंट द्या, whatever shear enforcement you may provide, the section is going to fail because the maximum value of shear stress tau c max is 2.5. समजलं का? So that is why first of all we check it from table number 20. If the condition from table number 20 is satisfied, then there is no need to revise the section, and then further we will see on to table number 19. Okay, so now as we know the value is 2.5 over here, we will go to our notes board. Okay, so tau c max it is 2.5 Newton per mm square. Now compare these two values 1.7 and 2.5, 1.7 and 2.5, who is greater? So I can write over here your tau v is less than tau c max. What is the meaning of this? So here I can write there is no need to revise the section, आणि तुमच्या माहितीसाठी सांगतो, आतापर्यंत आपण जेवढे काही बीम्स डिझाइन केलेले आहेत मागे सुद्धा टेबल नंबर 19 वरून आपण ज्या व्हॅल्यू घेत होतो, तुम्ही तिथे सुद्धा टेबल नंबर 20 ची व्हॅल्यू कंपेअर करून बघा tau c max ची व्हॅल्यू. tau c max ची व्हॅल्यू तुम्हाला नेहमीच जास्त मिळेल. ओके, तिथं आपण असं मी दाखवलेलं नाहीये किंवा ही स्टेप आपण तिथं केलेली नाहीये. ओके, कारण तिथं सेफ येत होतं आणि ते येतच, त्यामुळे आपण केलेलं नाहीये. यू कॅन ऑल्सो दिस स्टेप इनटू दॅट फ्रॉम न्यूमरिकल्स ऑल्सो. If it is not added, then it is also okay. But here it is required for shear reinforcement, because for the shear reinforcement in this combined bending and torsion, sometimes the value of equivalent shear stress is greater than the maximum shear stress. So in that case, we need to revise the section. But here there is no problem. There is no need to revise the section. Okay. Now after this, now again go to table number 19. Okay, so and find out the value of tau c, that is permissible shear stress. So from table number 19, okay, table number 19, tau c is equal to, so we need to calculate the value of tau c. To calculate the value of tau c, we need to know the percentage of steel. So the percentage of steel is 0.56%. This is our percentage of steel. Percentage of steel is 0.56%. So now we will go to the IS code again. Now we will go to the IS code. Here is the IS code. Okay. So we will go to the IS code and we want the value from here, this table, design shear strength of concrete. Okay, so here now 100 AST upon BD. So our value is 0.56. So our value will lie between these two values, 0.50 and 0.75. For M15 the values are given over here, 0.46 and 0.54. Okay, so this thing we must see these four values. Okay, these four values we should see, and we want it is for 0.56. What is the value? So let me know the value after interpolation. Do the interpolation. The answer is 0.479. 479 means I will take 0.48. Okay, so we will go to our this whiteboard. So here we got the value of this tau c is 0.48 Newton per mm square. Now we are having this value. Now compare the value of tau v and tau c. So tau ve is greater than tau c. Here if you see, here tau ve is greater than tau c. What does this indicate? What does this indicate? So this indicates that shear reinforcement is required. This tells us that shear reinforcement shear reinforcement is required. Okay. So the shear reinforcement is required. Your tau v, that is the nominal equivalent shear stress, your tau v nominal equivalent shear stress is greater than your permissible shear stress. Okay, हा difference लक्षात घ्या इथं. If your tau v is greater than, this is the maximum shear stress, आणि जर तुमचा tau v हा maximum shear stress पेक्षा ग्रेटर आला तर डायरेक्ट तुम्हाला सेक्शनच रिवाइज करावं लागतंय. इथं मग तुम्ही ते 10 mm स्टिरप्स वगैरे प्रोव्हाइड करून चालत नाही. तर काय करणार तुम्ही डायरेक्ट सेक्शनच रिवाइज करणार. म्हणजे 300 बाय 600 सेक्शन आहे तर तुम्हाला तो सेक्शनच बदलावा लागणार. Okay, whenever your tau ve, that is nominal equivalent shear stress, is greater than tau c max. Okay, हे लेस आलं म्हणजे there is no need to revise the section. पहिली गोष्ट कन्फर्म झाली. Next, what we have done, we have calculated the permissible shear stress from table number 19, and this value is 0.48. And what is the value of tau ve? Tau ve value is 1.7. Okay, so this tau v is greater than tau c. Tau v greater than tau c म्हणजे काय? Shear reinforcement is required. Means there is no revision of the section. Section आपला तोच राहणार 300 बाय 600 चाच, पण त्याच्यामध्ये आपल्याला shear reinforcement टाकावी लागणार. मग shear reinforcement टाकावी लागणार म्हणजे याचा अर्थ काय की आपल्याला stirrups डिझाइन करावे लागणार. Okay, now we have already assumed the bar diameter for the stirrups. Just we need to calculate the spacing of the stirrups. So here now shear reinforcement is required. So the shear reinforcement is required. So therefore you can write over here provide. So provide, we are going to provide two-legged 10 mm diameter stirrups. Okay, so now we will calculate the area of stirrups. Now ASV is equal to area of stirrup. So what is the area of the stirrups? You calculate the area of the stirrups now. Area of the stirrups, ASV is equal to what? It is 2 into pi by 4 into 10 square. The diameter is 10. Two-legged stirrups are there. So let me know the answer. What is the answer? Calculate it and drop the answer in the chat box. 2 into pi by 4 into 10 square. This is the area of the stirrup. Let me know the answer fast. Okay, so the किती आलं 157.079 157.07. Okay, so the answer is 157.07 mm square. So this is the मुद्दाम करता का. So this is the area of the stirrup. So now calculate the spacing of the stirrups from this area. Okay. So to calculate the spacing of the stirrups, we know that ASB is equal to, what is the formula for ASB? So for transverse enforcement from IS 456-2000, we know the formula. We know the formula that AS is equal to, that formula is TU into SV whole divided by B1 D1.87 FY, okay, plus VU into SV whole divided by 2.5 D1 into 0.87 FY. This is the formula. So from this formula, by using this formula now, we are going to calculate the spacing SV. Okay. By using this formula now, we are going to calculate the spacing SV. SV is nothing but the spacing of stirrups. And we want the spacing of these stirrups, two-legged 10 mm diameter stirrups. We want the spacing of this by using this formula. So here two new terms are there, B1 and D1. Okay, you don't know how to calculate the B1 and D1. So B1 and calculation of B1 and D1 is very easy. You should calculate the center to center distance. Okay, center to center distance of the reinforcement to calculate B1 and D1. So we will see now how to calculate B1 and D1 now. So here, now this is our beam. I will draw over here. This is our beam section 300 by 600. Then again, here the stirrups are placed. These are the stirrups. Okay, so now, so here the stirrups, I think it is not up to the proper mark. So stirrup should be from this point. Okay, so these are the stirrups. Okay, and at the bottom now we have provided three bars of 20 mm diameter, right? So I will show those bars. So at the bottom our three bars are there. This is first bar. Here it is our second bar. Here it is third one. These are the three bars of 20 mm diameter. And top we have provided two bars of 12 mm diameter. Two bars of 12 mm. So the meaning of B1 is, so if I tell you what is B1, then the meaning of B1 is, so this distance, this is nothing but B1. This is B1. The center to center of these two bars is nothing but B1. Okay. And what is D1 now? So again, center to center of bar sheet vertical direction. So if I draw the lines again, then if you see, this is the horizontal line. Again from this point also one line. Okay, and if I join these two lines, if I join, so this is nothing but your D1. This is nothing but D1. Okay. Now we know that we have assumed the cover as 25 mm. Okay. So from this side, see, from all the sides, the clear cover, this cover is 25 mm. From this side also clear cover is 25 mm. From bottom also clear cover is 25 mm. From top also it is 25 mm. From all the sides your clear cover is 25 mm because we have assumed our clear cover as a 25 mm. So I will write over here. So still for your understanding I will show over here. This is 25. Okay. From this point also, from this point to this point, this is also 25. Okay, from here also, from this point to this point, here it is also 25. Okay, so this cover is 25. From top also the same case. For here, the clear cover is 25. Okay, fine. 12. So it is 25 mm. So now we will calculate this B1 and D1 now. So B1 is equal to, so B1, if I now calculate the B1, so B1 is equal to, just see it is not much more difficult. So this total is how much? Total is 300. We know the width of the section 300 minus. आता मी या बाजूने येतो पहिल्यांदा. मग इथून ते इथपर्यंत 300 आहे. So I will start from this and see here. From this point to this point. This total is 300. Now I will start from this end. I should minus this much distance from this left end and from right end also this much distance I need to minus. So I will get this value B1. So for that purpose now what I should minus first 25. Okay, this 25 from this side. Then the diameter of this stirrups bar, that stirrups bar is 10 mm, so minus 10. Then again minus how much it is, this bar diameter is 20 mm. Okay, these bars of 20 mm. So it will be center of this bar, so it is minus 20 by 2. 20 by 2 म्हणजे मी या पॉइंटला आलो. Right now I come to this point. Okay, I come to this point. I subtracted from this end. Now same thing I should do from this end also. Okay, so now I have subtracted from this end and I come to this point. I have minus this 25. I have minus this diameter of the stirrups. Then I have minus this half of bar diameter. Same thing I should do from this side also. Okay, so for that purpose now again minus 25 from this side. Then again the diameter of this stirrups. So again minus 10 and again minus 20 by 2. Minus 20 by 2. Okay, so B1 is equal to, therefore B1 is equal to, what is the value? Let me know the value. Up till now I will calculate D1 also. What is the value? 210. Okay, so the value is 210 mm. Okay, now after this calculate D1. So from this point to this point. So I will do that. So here minus 25. Now I will come from the top first. So at top the clear cover is 25. So minus 25 म्हणजे मी या पॉइंटला आलो इथल्या. ओके, हे बघा minus 25 टॉप पासून आलो, minus 25 केलं की या पॉइंटला येईल. तर इथनं मग हा हॉरिझॉन्टल बार डायमीटर आहे 10 mm चा, तो मायनस करावा लागेल आणि त्यानंतर हा बार डायमीटर हाफ ऑफ टॉप बार. ओके, सो 25 मायनस 10 हा स्टिरअपचा बार झाला मायनस 10 मायनस टॉपचा बार कितीचा आहे 12 mm चा आहे, सो मायनस 12 by 2. Okay, so I came at the center here. I came at the center. Now minus again from bottom also I need to do the same thing. From bottom also I need to do the same thing. So I should minus first the clear cover, that is 25 mm. Then this horizontal bar of the stirrups, that is 10 mm. Okay, and then half of this bar diameter. So it will be again minus 25 minus, so what is this bar diameter? It is 10 and minus 20 by 2. Minus 20 by 2. So therefore D1 is equal to The answer is 514. So the answer is 514 mm. Okay. Okay, good. So now today we will stop over here. In the next lecture now we will solve the problem further.